Welcome to Lecture 10. We have been through a lot of details here about how the basic elements of the climate, whether it's warming, why it's warming, and what risks we might be taking. In this lecture, we're going to start talking about what we can do about it. At first, I'm going to depict some of the challenges of the problem, kind of dimensioning the problem in a way, and say some things about possible actions. There will be a Lecture 11. Aren't you happy about that? There will be a Lecture 11, and Lecture 11 will be a proposal. I thought for all this time I should have an opinion. So I have put together a proposal with a lot of other people's discussion. It's not guaranteed to work. It's an idea. Kind of a straw man proposal. And then we will do in Lecture 11 a big sort of a short summary of the course. So let me try and share my screen here so we get right down to this lecture. I believe that's the right one. Yes, what can we do? And if you feel like this guy, what can I do? I just put this in because I thought I'd pause for a second and say that there are many things individuals can do. You can compost your garbage, eat less meat, buy a more efficient vehicle, upgrade your air conditioning to a higher SEER, higher efficiency system, all of which use less energy and less emissions. And if everybody did these things, it would help. However, I don't have a series of slides that have a list of things you can do. I think that even if a lot of us did those things, we would find that there's still a lot left that needs to be acted on in a collective way, having to do with the way we generate electricity and the way we transport ourselves around. I, like everybody else, lives in a modern world, and I take advantage of it and use a lot of energy. And so that's where we are. And I'm not saying we should not have some individual responsibility to change, but and we should all move in some direction like that. But I think there are large issues that have to be taken care of collectively. So there is some role for government, both local, state, and federal, as well as international cooperation and leadership, hopefully by the right countries. So we'll move on from what can I do. So I would like to spend a little time on the challenging dimensions of the problem, just so we understand kind of more about what's going to be needed. This is CO2 emissions by country in 2014. 2018 or 19 data would not look that much different. The numbers would move around a little bit. What this says is the top 20 countries contribute 75% of the emissions, CO2 equivalent emissions. You can see here that I have not grouped together the European countries into the Eurozone. If I did that, they would be kind of third on the list behind the United States. However, they're all on different paths of emissions with different energy strategies, and so I kind of left them spread out. You can also see that the United States and India, India, the United States, and China are big contributors, and in particular, the developing countries, India and China, are going to be very important to the future of this problem. And because they are clearly developing countries, there are people who are growing in prosperity in those countries, and so there's just more happening there. And they both have large deposits of coal, which is one of the worst emitters, worst fossil fuel emitters that there is. And so there's a lot of issues there. The total global emissions in 2017 was about 49.4 gigatons. I have used 50 gigatons in various discussions in the lectures we've had as a round number. That number bounces around a little bit by year. It had been kind of flat for a while. Last year, 2019, it actually went up by a few gigatons. That's kind of where we are. The next slide shows population projection. This is done, I believe, by the US Census Bureau. They have an international division. This is the international database. The population is on the left vertical axis. The birth rate is on the right vertical axis. The blue diamonds are actual population. As you go across population to I don't know if this goes up to 2018 maybe, and you pick up the population curve there, the square gray blocks are a forecast, right? A principal element of that forecast is the orange triangles. The data before 2018 or so is actual historical birth rates, a peak around 1960 something. This is for the globe. Since 1960 or so something, around that time, the birth rate has gone down. And of course, what you see beyond 2018 is a projection of the birth rate into the future. Now this, what you should know about this is that the current world average for emissions is about 5 tons per person, right? So this projects, this particular population projection, which is a bit on the optimistic side, or at least on the low end, I should say, whether you view that optimistic or not, is about 9.3 billion people on the planet by 2050 from today's 7.5 billion or so. These are round numbers. I'm sure they're not completely accurate down to the person. If you do that, you're sort of adding about 0.33 gigatons per year to the total emissions, so that by 2050, instead of 50 gigatons per year, we would be adding 60 gigatons per year. So maybe another 10 to 15 gigatons would come from the population addition, right? By the way, 5 tons per person is the global average. I believe in the US we're 12 to 15 tons per person we're per capita. So we're a lot more. Europe is a lot more efficient than we are, partly just because we have population spread over a larger area, larger temperature regime, and more movement over longer distances. We do a lot of transportation distance. Okay, so a lot of this population forecast depends a little bit on what's going to happen in Africa. Depending on social, cultural, and political issues, Africa could go at a lower birth rate and end up with this kind of population forecast. I have seen population forecasts that go as high as 10.5 billion people by 2050. So another thing to look at is what are the sources of global emissions? The graph on the left, so if we go with the 50 gigaton round number, the graph on the left, the y-axis is in gigatons of CO2 equivalent. So you see that energy in its various forms, the way we use energy in various forms, is 36 of those 50 gigatons. So a lot of it is energy production. There are various industrial processes that contribute 11 gigatons. For example, cement, making cement contributes emissions to the atmosphere. Agriculture, when you pour fertilizer on a field, you get nitrous oxides that come from the nitrogen in the fertilizer combining with oxygen in the atmosphere. And then land use, of course, when you tear down a bunch of trees or something like that, or even when you deep till an agricultural field, you release carbon from the soil. if you tear down a bunch of trees, when the trees decompose, they decompose, one of the things they decompose into is carbon dioxide. Now, that's a very large breakdown. If you break down just the energy, the energy conversion here, you can see that of those 36, 16 gigatons come from electrical production. 9 are actually burned in industry. So, for example, in the metals industry, we burn a lot of natural gas to run furnaces that anneal steel and aluminum and other products. And then, of course, energy is used in transportation. A lot of energy is used in transportation. About, I think, the majority of that 7 gigatons is people in light vehicles. Certainly in the United States, that's a true statement. And then, of course, buildings and other type edifices consume 4 gigatons. That would be for energy produced in buildings for heating and cooling, so a boiler plant for a university or something like that. Now, that's 2017 data. This is from a different way of, there are many ways to segregate emissions, right? And so I'm always cautious that once you look at them one way, like we just did back here, sometimes it helps to look at it a different way. This categorization of emissions has been done by the Gates Foundation. We all know Bill Gates, the Microsoft founder. And Bill Gates talks about 5 categories, and being a kind of optimistic guy, he talks about ideas that we need to have in all 5 of these categories. So he points out that electricity transmission is about 25% of the problem. If we go back here, we have 16 out of 50. That looks like more than 25% to me. That's more like 32%, but we're in the ballpark, right? These are rough categories. Then he has an interesting couple of categories here. Agriculture, he points out, is over 20%, something like 24% of the emissions. Now, I would warn you that it all depends on what you call agriculture, but there is a lot of emissions from fields. There's a lot of emissions from fields, for example, nitrous oxides, as I said, from fertilizer, from releasing carbon into the atmosphere. Agriculture also uses a lot of energy in the form of red diesel. Red diesel is something that tractors use. Obviously, in a large-scale farm, there's a tremendous amount of equipment running around, which burns a lot of fossil fuels, non-electric equipment, so on. Manufacturing, as we said earlier, manufacturing uses a lot of natural gas and other type fossil fuels. And of course, transportation, which uses a lot of oil and gas. Buildings, which use commercial buildings, certainly, and other buildings. And finally, he has a category called miscellaneous, which I think he sort of says, well, that's the rest I couldn't categorize easily. But his point, and it's actually worth, if you want to go look at gatesnotes.com, you'll find an interesting discussion that he does about climate. He's invested in various climate technologies to work on the problem. So this is a different way, kind of a different way of looking at where the emission's coming from. So let's take a look here at the trajectory to 2 degrees. So here are 3 paths that are emissions paths going forward. So here we are, 2020, maybe 2019, at about, actually this one shows us up at 60, but let's say we're in the 50s, right? And this path up here with the blue diamonds, the connected blue diamonds, is basically what we might call the business as usual path. So we've talked about this several times. This is the path that it's a scenario built by a bunch of folks who are looking at the way we conduct business today and our lives. And if we just keep doing what we're doing, they're proposing that this path, this blue diamond path, is the way we would end up emitting out to 2050. And we're kind of on that path. Now, Paris is the gray boxes. So you can see Paris is just saying, please keep everything constant till about 2030, and then try and not go so steep. Maybe go up a little bit. Now you've got to 2040 to turn on technologies that you know, might help reduce emissions, and then go fairly flat again, right? And that's kind of a description of the Paris Agreement. Here is the 2-degree pathway. So the 2-degree pathway says at 2030, you've got to be going down pretty steep. Think about where you got to here in 2050. We are at about 23 or 24, actually 23 gigatons, right? So it's saying you're starting above 50, you're going to stay constant to sort of 2030, and then to stay on the 2-degree pathway, you need to get down by 2050 to about half or less, slightly less, maybe 40% of our emissions that we have today. If you look at that curve, if you look at the difference between the 2-degree pathway and the business as usual curve, the business as usual curve emits from 2020 to 2050, it emits about 2,300 gigatons. If you just add it up each year, right? About 2,300. The 2-degree pathway emits about 1,300 gigatons. So the difference is another 1,000 to 1,100 gigatons, right? So what it says is we need to somehow over the, you know, you can look at the trajectory by year, but if you don't look at it by year, if you just say between now and 2050, what do we have to do to stay below 2 degrees? What we need to do is we need to cut our cumulative emissions over that time by half, by a little more than half. Or we have to find emissions savings, if I can use those words, of let's say 1,100 gigatons, right? We need to go find those kind of savings. Now, this is basically the same as the story that I told you here. You would hope that I would be reasonably consistent, wouldn't you? I know that we've been over this graph a lot, so I'm not going to spend a lot of time here, but you see the 50 gigatons coming in that we're pumping into the atmosphere. You see the ocean and the biosphere helping us out, the mantle trying to act like Mother Nature and bury some carbon for a long, long time. And you see that we are at 3,000 gigatons, and if we go to, 4,200 or something, if we add another 1,000 or 1,200, we're going to be at 2 degrees, right? So the 2-degree curve says you can add about between 1,000 and 1,200, which is what I said before. Now, the business as usual curve is going to take you to a much higher temperature because you're going to add a couple thousand to the current level of 3,000, right? So what we want to do is we want to look as we go forward for opportunities to find ourselves limiting our emissions over the next 30 years between 2020 and 2050 to something like 1,000 to 1,200 gigatons of carbon dioxide equivalent. Okay. So what kind of strategies do we have to do that? So these are strategies for action. There are 3 that are here, and I'm going to talk about these. I'm going to expand on mitigation and adaptation quite a bit. I'm going to dispense with geoengineering as soon as we finish this slide, and I'll tell you why in a second. So mitigation is defined as any sort of actions, regulation, market-driven, R&D type actions, that technologies that may occur in the future, anything that will reduce emissions or capture carbon in either at its source or out of the atmosphere, right? Thereby reducing the amount of carbon dioxide and other greenhouse gases in the atmosphere. So basically, we want to do various strategies over all these source categories like energy, agriculture, industry, and so on, buildings and so on. So we reduce emissions, and we want to perhaps develop these things called NETs, negative emission technologies, which we're going to talk more about later. Now, adaptation says, well, we realize that even if we get good at some mitigation, we're probably not going to solve the whole problem. We've already baked in probably a whole degree or more, some would say a degree and a quarter of temperature change. We've experienced about a degree since the Industrial Revolution, maybe about 0.8 centigrade, maybe about 0.8 degrees centigrade. Remember that when I say a change in centigrade, just double it to get a change in Fahrenheit. It's actually 9/5 if you want to get fancy, but double it, it's easier in your mind. It's easier to do that. And there's enough uncertainty here, you wouldn't be far off. So since 1950 to 1970, kind of a baseline, we've seen a 0.8 degree increase in centigrade temperature, global temperature. So we're saying that's already there. We're obviously going to get more temperature increase by 2050. And so how do we adjust so that we're less sensitive to temperature? In particular, all the effects we talked about in the what are we worried about part, where we said these are the things that are sure to happen. Sea level is going to go up. We're going to have more extreme weather. We're already having more extreme weather, but we're going to have even more. We're going to have to redesign cities to make them more healthy to live in very high temperatures, especially cities in warm areas, and various other things, right? We're going to have to adjust and become more resilient, adapt to temperature and precipitation changes so we're more resilient in agriculture, for example. We may well have to move chemical plants and power plants further off the coast, as some of our infrastructure built near the coast will be affected by storm surge, sea level rise, and so on. So that is called adaptation. I'll show you some more details on adaptation in a second. Geoengineering says if we think of the system of the Earth, the climate system, the Earth is itself a system, is there a way to engineer a system of some sort that would reduce the effect of putting the way we're affecting the global temperature? So we are busy putting CO2 in the atmosphere and temperatures going up. However, we've built a culture around this kind of thing. So is there a way to engineer some change that might allow us to rebalance some part of the equation? So a couple of ideas have been put out there. One, let me just mention two ideas associated with solar radiation management. You could put aerosol particles up in the stratosphere and reflect sunlight so that you reduced the solar irradiance or the solar intensity on the Earth's surface. So you remember we talked about the global average of 160 watts per square meter is absorbed by the Earth's surface. 100 watts per square meter are reflected from clouds and from the surface and so on. Well, what if you could just reflect more energy up in the stratosphere so it didn't have a chance to warm the troposphere or be absorbed by the surface? So it turns out that this is a very doable technology. However, it brings up all kinds of questions, like who would manage this? What if one country went off and did this? What would the other countries say? Is there a way to do this in such a way that you would do it by latitude so you would end up in a kind of climate warfare situation? Is inter-country politics such that we could actually cooperate on such an idea? And how would it be managed? And then there is the problem that we're still putting CO2 in the atmosphere, so the oceans are still becoming more acidic. And the oceans are 7/10 of the Earth's surface. So that means they're not warming as much because they're not receiving as much energy, solar energy per square meter because of the reflection in the stratosphere. But they are still absorbing CO2, so they are still getting more acidic, which would cause a lot of problems. So there are other problems you're not managing. In addition, various people have done some engineering studies of this with climate models and suggest that one of the things that might change in this grand experiment is that you might have some serious effects on precipitation bands. In other words, depending on how you distributed the aerosols, you could move precipitation zones around the Earth and change deserts and location of deserts and agricultural zones and so on, which would be a very serious thing to get into managing. So that's one idea. Another idea is to put mirrors, solar mirrors out into space at Lagrangian points. These are orbital positions where basically you could put a large solar mirror and it would stay there without a lot of maintenance. It's kind of a stable point in the Earth-Sun gravitational system. Of course, that has some of the same issues, although it doesn't require constant management. You can imagine if you spray particles in the atmosphere, they eventually fall out and come down to the surface of the Earth. Of course, that is a problem too. What are all these aerosols going to do to us coming down through the atmosphere? But you wouldn't have that problem with a mirror at L1. And so there might be some advantage of this over this other idea, which always struck me as being crazy, putting aerosol particles in the stratosphere. Now, also, another kind of geoengineering, technically speaking, is something that I think we really do need to think about, which is removing greenhouse gases from the atmosphere. The idea would be, this is basically a negative emission technology. The idea would be to suck up large amounts of CO2 out of the atmosphere with big fan type systems. And then basically you would be imitating the weathering thermostat. So you would take this CO2, kind of spray it over the top of igneous rocks so that it would form calcium carbonates, and you would essentially mineralize the carbon, thus capturing it. So you don't have the problem of carbon capture, which is talked about, where in a gas plant you capture the carbon dioxide and the flue gas and you take it in gas form, try and compress it and store it in like an underground reservoir. Here what you're doing is you're taking the CO2 out of the atmosphere. You're actually imitating the weathering process by, in a sense, exposing it to ground up igneous rocks, and then having it mineralized. So you're sequestering it through mineralization, turning it into a solid, or helping it participate to become part of a solid, which is a really cool idea. People have actually done this on small scales, believe it or not, and it's been successful. It's very expensive at the moment. I'm going to throw out a number that I saw a while back. I have no idea how accurate it is anymore, which was $100 a ton of CO2, which is, of course, with gigatons of CO2 to remove, that would be a lot of money. Right now, not a technology we can think too much about, but something we should be working on. Okay, well, let's talk some more about mitigation and adaptation. So mitigation has a list of things on the left, which are supposed to be suggestive. They're not the only things you could do. And if you think about those things, they're all driven around the idea of reducing emissions, less emissions going into the atmosphere. So transportation is sustainable. That might be electric vehicles, provided electricity was generated with non-carbon sources. Conserving energy, you can always use less energy, which means the energy you didn't use didn't generate any emissions. Building code changes, the same kind of energy efficiency. Renewable energy, converting energy like electrical production to solar and wind, let's say. Deep lake water cooling, we could take deep lake water, which is cold, and use it to cool, air condition. Vehicle fuel efficiency, this goes back up to conserving energy, and so on. There are many more you could list. Over on the right are adaptions. These things do not reduce the amount of CO2 you're putting in the atmosphere or the amount of CO2 equivalent. All these things do is prepare you for the things that can go wrong when the temperature increases. So we would upgrade infrastructure like sewers and culverts to help handle extreme rainfall. Residential programs about sewer backflow, health programs. If we're getting more exposure to vector-borne diseases, we can fund more health programs to find out when people are having these problems and letting them know when these diseases are around. Emergency and business planning, help for vulnerable people. Then in the middle are things that kind of fall in the category of both. Solar thermal is going to save energy as well as be around when you need it. And tree planting helps. Local food production, so you're saving the the transportation costs of bringing food to you, and so on. We won't go through all those. So that gives you a feeling. Now let's talk about just mitigation, which I'm going to spend a little bit more time on here, because this is where we can make, I think, a big difference. There are several ways to go about this. One is policy. And what I mean by policy is a set of things like carbon taxes, incentives, standards, and regulations. You know about most of these things. Carbon taxes, I'm going to explain in a minute an example of a carbon tax. But basically, they put a price on carbon so that people who use it would be paying more and would be motivated to use less of it or to switch to some other way to get the same service without generating carbon. Economists are really fond of this. And if you look at the Nordhaus book, this is his #1 idea for working on this problem. There are all kinds of incentives. You could give people what are called freebates and rebates, which means, say you go buy an electric vehicle, you get a couple $1,000 check, or you get a tax credit in the first 3 years after you buy it, or those kind of things. We have incentives for solar panels, or at least we used to. I think they're ending in a year or two, and things like that, right? Standards. We have appliance standards for HVAC, for various types of appliances, refrigerators and dryers and so on. And the idea behind appliance standards are to let people know that there are energy efficient devices out there that they can pay for and will return a value to them over the lifetime of the appliance, right? And those details are available for the consumer to find out. Local goals means local communities can set goals for planting trees, green space regulation, even emissions from their local utilities. Various states have set emissions goals for utilities. New York, California come to mind. Regulations. We have federal regulations like the CAFE standards. Unfortunately, the current administration has gone backwards on CAFE standards. Methane leak regulations, they've also taken that one off. And we'll talk about those later, but they are a form of policy. Now, there are free market actions that take place even without government intervention or populist movement to support. There is a move to renewables. I have solar panels on my house in New York. I did that partly because I'm kind of a techie wonk and wanted to see how it worked, but partly because it has about a 10-year payback. They're good lifetime for probably 20 years, 25 years. And so they will pay for themselves at some point. Coal plants are closing. You may have heard that. A lot of them are converting to natural gas because natural gas is so inexpensive. Coal has just become uneconomical for lots of reasons. And most coal plants inside the United States are going to go away in 10 years. However, coal in India and China and East Asia is on the rise, and we need to do something to support its conversion to some other fuel. But the market may eventually go that way. Hybrids are very efficient cars. There was something like a $3,000 premium on a hybrid over the same model as an industrial combustion engine. However, today that premium is down to like $1,200. I bought a hybrid in 2012, which you had to drive for 100,000 miles to pay off the premium. Today, you would only have to drive that car for less than 50,000 miles, maybe 40,000 miles before it would pay off. There are more and more electric vehicles out there. If you use electric vehicles, they're a fun car to drive. They have a great amount of torque. They handle really well. They are going to be much more efficient and much lower maintenance. The problem today is if you plug them into your electrical outlet is not necessarily a low emissions outlet depending on what state you live in. So we have to worry about how our electrical power is produced. And there are lots of reasons to upgrade your appliances and your heating and cooling because you can get payback over time. Also, there are long-term infrastructure investments we could make in energy storage and smart grids and other things that would improve the transmission of electricity, improve the way we use electricity at different hours of the day, that would make a difference to this problem, a substantial difference to this problem. And then, of course, we need to invest in R&D, research and development, to support other technical changes, which will make it easier in the future to reduce our emissions. Okay, so now I want to talk briefly about a bill in Congress. It's called H.R. 763. It's the Energy Innovations and Carbon Dividend Act. I actually lobby Congress to support this bill in an organization called Citizens Climate Lobby. And if you're interested in that organization, you can go to the website shown at the bottom of the page and join as a citizen. The idea is that that you would impose a fee at the source, basically for a carbon fee, sort of starting at maybe $15 a ton. In other words, you would collect it from the person who had the mine or the person who had the gas well or whatever. And you would pay a dividend back to all United States households, all citizens in the United States. And you would also have a border adjustment, which would add fees for imports from countries who do not have a carbon fee. So some country is making the same product overseas that you're making here, and it's a carbon intensive product and you're paying a fee, then you want to make sure that that gets equalized. So you have to have a border adjustment. The assumption is that if we make, let's say, an oil company pay a fee on oil produced, they would pass those costs on to the consumer, right? That's why we pay back a dividend. Basically, we're taking all the fees, and apart from a couple percent administrative overhead, sending people checks each month to disperse this fee back out to everybody, right? So let's go through a little bit of arithmetic. The idea behind this particular bill is it starts at $15 a ton, increases by $10 a ton for 20 years. It's levied at the source, the well, the mine, or the port, wherever. And the dividend, all the revenue, all the net revenue goes back to the household. So $50 a month for a family of 4 with 2 children. And in 20 years, it would be $400 a month. Basically, you get 1 share for each adult and a half a share for each child. So basically, you just send it back, right? The idea is that people would quickly realize that you need to switch as much as you can, reduce the energy you use, and the check coming in could actually turn into a profit, or at least pay your bills, right? Wealthy people use a lot more energy than other people do, and so it's a bit of a progressive refund in the sense that people who don't use much energy, don't travel overseas, don't have 3 cars, that kind of thing, they will get money back that will help them pay their bills, whereas some of us who do a lot of that kind of thing will end up losing money in the proposition, but that's probably good. And we will all be motivated to be more efficient. And this is an example of a simulation that says what would happen over time. We would get a 52%, if we implemented this thing in 2015, of course, which we haven't done, so it's a long time in the past. We would get a 52% reduction in emissions in the United States by 2035, right? And here's the cost to the consumer, the average tax burden. This is at $15 per ton. So if you think of yourself as being, let's say, in the middle quintile, for the various ways that you would pay for this in terms of utilities, gasoline, and other services, food and drink, and so on, you would be paying $219 net benefit. This would be the tax burden that you would be paying each year for this tax at $15. Now, of course, that's going to go up every year by $10, right? So at some point, it's going to be a big number. But remember, you're getting the dividend back. Now, there's lots of reasons why a carbon tax is perhaps a good idea, and economists think of it as a free market solution to the problem, and many conservative economists are fully behind this idea. I should say there are issues with these carbon taxes. The problem of raising the fee every year can run into political issues where people go, I just don't want to pay this anymore, even though I am getting a dividend. You could get a backlash after a number of years, and the carbon fee can be held to a point where you don't get the emissions reductions. This has politically been done, and this particular carbon tax strategy has been used in several countries already, and they've run into these kinds of problems with the politics of raising the price each year. Nordhaus suggests that we start out at a number that basically guarantees emissions reductions. So he suggests $40 to $50 a ton is the right number to start at, which would take this to about 4 times the cost. So if you want to think again of yourself in quintile 3, let's say $252, you would be paying 4 times that in additional cost, but your dividend would come back and pay for, if you're in the middle there, almost all of it actually at quintile 3. Now, when you get into 4 and 5, you'd be losing money. But it is a free market way to incentivize people to move to less carbon consumption. Now, the next slide here, I do a series of calculations, and I was trying to just sort of say, what are the real opportunities here in terms of size? So these are real back of the envelope, I warn you, real back of the envelope calculations. I looked up a lot of parameters and just tried to see if you thought about that 1,000, 1,100 gigatons we need to find, we need to reduce our carbon emissions between now and 2050 by 1,100, let's say, gigatons. where would we find them, right? So I looked at various categories just to see how big they might be. The savings column is in gigatons. The scenario or the action, if you want to think of it that way, is in the middle. And then I put a sector or category to the left. And you can see if we took all of the electricity generation in the world and we made it from non-carbon renewable, well, non-carbon, not necessarily renewable. So we're going to make a distinction between power generation that's non-carbon, for example, nuclear. Nuclear is non-carbon, but it's not renewable. You have to provide fuel. Very small amounts of fuel, but you have to provide fuel. So small amounts in terms of pounds, right? It's not like coal where you have to supply tons to generate megawatts. So all non-carbon by 2035. So this says you would put a ramp on by 2035. You would be all over the non-carbon, and during that time you'd save a little, and then from 2035 to 2050 you'd save a lot. You get 550 gigatons, so you get half of what we need, right? And then you can see smaller things. If you replaced all the coal in the global world with non-carbon, you save 400. If you replace all the coal with natural gas, you save 280. Coal has in the fuel, in the nature of the fuel itself, it emits twice as much CO2 as natural gas. So natural gas is a considerable improvement in emissions. However, the problem with natural gas, which we'll talk about later, is methane leaking during the production of natural gas. You just replacing the remaining U.S. coal plants with non-carbon has an effect, not a huge one. If a lot of people put renewables into operation in the next, so years ago, you get 20 gigatons. That's a scenario created by the Energy Information Agency. Most people think that renewable scenario is very conservative, but let's just say I used it to figure out if we replace that much electrical production with renewables, we'd get 20 gigatons of savings. Then you get down to light vehicle transportation. In the United States, light vehicles represent some 70% of the emissions. A little surprising since there are a lot of freight trucks out there and they don't count as light vehicles. But if you replace all the world vehicles with electric vehicles and you use a number like California's current emissions to generate electricity, you get 170 gigatons. If you were to take the current electric vehicle forecast, that is done by the Energy Information Agency, and you double the mileage of existing cars, new cars. So you have some electric vehicles and new cars with a mileage of about 40 miles to the gallon, which would be like a good hybrid is today. You would get 120 gigatons. If you double the mileage for all world light vehicles, you get 90 gigatons. And then you see some other numbers there. If you did carbon pricing in the US, given that simulation that I showed you, you get about 70 gigatons. If that whole thing applied to the world, you get 225. That's a huge leap. It's really hard to know how you would apply that strategy to the world, but that's what you get if you just do it. Buildings you can make more efficient. Buildings do get more efficient every year. We're motivated by the free market desire to reduce our costs. This, I think, is a conservative estimate of what would happen almost just by free market, but we could incentivize it even more of 100 gigatons. Just by installing LED lights in residential homes and doing a better job than we're doing, we would get 10 gigatons. If we ate half the meat that we eat today, that we project to eat by 2050, we would get 75 gigatons in the world. There's a lot of emissions come from beef consumption. And if we reduce methane gas leaks, which I'll say more about later, this is a rather large reduction and I'm using an estimate of leaks, which is a little hard to know today because we haven't got a good measurement system for them. But there is a number there like 25 gigatons. Okay, so there is some samples, right, of ideas. And how do you do those calculations? I'll just give you a very quick primer just to say they're not hard, but there's a lot of, as I said, back of the envelope assumptions. What you have to do, so the 2050 line, the blue diamonds, is a forecast of electricity generation between looks like 2017 and 2050. Okay, so you go to the Energy Information Agency or one of these international energy agencies, and you look up what they're forecasting for electrical production up until 2050. And those forecasts are out there, and they make all kinds of assumptions you don't want to get into questioning. You just take it, right? Then you say, coal currently generates about 72% of our electrical generation in the world. Now, that's the world. In the United States, it's a lot lower. It's like 30% and going down every day. So basically, you take 72% of that curve on top and you get the gray boxes, right? And then you say, let me convert coal to renewables along the basically where you see coal to renewables is the orange triangles. And you can see that I have started in 2020 converting coal plants. And by 2035, I've converted them all, right? So I've basically taken coal out completely. And when you do that, you get the savings is the light yellow, right? And you get this light yellow savings. So for all these calculations, you have to say, for example, meat consumptions. What's going to happen between now and 2050? Where do you cut it in half? How long does it take to make the transition? When are you done with the transition? And how much savings would it have, right? So you say, if I cut my meat consumption, I also have to know how much emissions come from supplying a pound of meat to a human sitting at a table in a restaurant or a kitchen who's eating a nice steak, which is starting to make me hungry. Okay, so that's how you do these calculations. And I must say that it was fun to go through and do all those, but it was time consuming. And you should really take them as round numbers. I would not sit here and defend them down to the gigaton. Okay, so what are some limitations of a whole bunch of plausible actions we could take? And I'm just going to share with you a list of some of these as we end this lecture. So as we know, solar and wind are intermittent power sources. Now, solar and wind cost per kilowatt hour to produce energy has gone down dramatically. And in fact, if you just looked at using solar and wind, almost all the energy productivity that's being added, all production capacity that's being added today is being added in solar and wind. Now, it's still very small percentage of the total electricity produced. But, so it's very cost competitive. But the problem is the storage, there's no storage cost added in there, right? So the fact that you have variable supply limits the amount of renewable source you can add to a power grid. If we, this is, when I say variable supply, I don't just mean night day. Of course, if you're, the wind works when the wind is blowing, which has to do with weather systems. The sun works when it's clear and the sun is up, which of course is only half the time. So you have to get through the night, even though we use energy at night, electrical energy. And you have to get through, let's say, an overcast winter in the north, or winter in the north where the sun angle, the angle to the zenith angle of the sun is very low on the horizon. So it's very hard to generate. So that means we have to get good at storage. Otherwise, we're going to be very limited, right? Solar also consumes a lot of space. I did a very rough and ready calculation that said if you tried to supply all the energy used in the United States with solar, you'd need the area of Texas and part of California in order to do this. So that says you can't just use the ground space. You've got to use distributed solar on rooftops and other kinds of things, which means generation is not just in big utility plants, but it's out there on Pat Love's house in Waterport, New York, which means we have to have a smarter grid because we have to supply him with energy in the winter when his solar panels aren't working. And that is a technology that's being developed, but it has a ways to go to be efficient. Natural gas could be a transitional fuel to replace coal. That is, natural gas still generates significant emissions, and someday we have to get off it. But for the next 20 years, it would help us a lot if we could get rid of coal. The only problem is in production, we have a lot of methane leaks. The industry says the leaks are below 2%. But if you get up but a lot of other measurements that are made by independent folks show leaks much higher than that, sometimes as many as 8 or 9%. There's a big debate going around about this. There's an Environmental Defense Fund satellite that's being launched in the next year, which will measure our methane leak rates around the globe a lot more carefully. This is something where we should have a regulation. The regulations have been, there was an emerging regulation on this. They have been stepped back from by the current administration, which I think is a big mistake. If methane leaks get above 2 to 3%, then there's no advantage to replacing coal with gas. And natural gas becomes a very dirty source at that point. We would really like to preserve the nuclear reactors we have. The United States, around the globe, the United States produces about 20% of its electrical energy from nuclear. They're non-carbon. They have been quite safe. There is a political issue with nuclear, which is a problem in terms of adding, and there's a cost issue. So there's political reaction against adding nuclear in my backyard, but there's also a cost issue, which has come out of very bureaucratic regulations in the United States. South Korea builds nuclear reactors for about 1/3 of what we build them for in the United States. There are Generation 4 reactors that will be available 10 years from now, maybe. They provide big steps forward in technology. There are sodium-cooled reactors. You know that the current reactors we have are water-cooled. And if there's a concern about safety, it has a lot to do with the reactor overheating, the water not being available. Those accidents that have occurred around the world have occurred because of containment, water leakage, that kind of thing. Sodium-cooled reactors or salt reactors are extremely safe. Basically, if something goes wrong, the reaction just shuts down. There are also small modular reactors that are, you know, if you build a nuclear reactor, it's typically 1,000 megawatts. Small modular reactors, which could be made in factories and distributed, are 60 megawatts or smaller. You could have very low cost. You could buy one of these, let's say, to power a university campus or a hospital system or something like that. We're going to probably need something like nuclear in northern latitudes. It's going to be hard to do it all with solar and wind in northern latitudes where we just don't have sources of that kind of energy, enough energy like that, especially in the winter months particularly. You heard a lot about biomass. Biomass is not carbon free. That's because you have to grow the materials. Now people say, well, you grow biological materials and they absorb carbon dioxide from the atmosphere when they do that. So when you burn them, you just put back what you took out, except growing them puts a lot of net carbon emissions into the atmosphere to run tractors, irrigation systems, leach the soil, all that kind of stuff. We need a much better understanding of net carbon emissions with biomass as an energy source to really go to that as an energy source. Carbon sequestration is something people talk about all the time. This would be something you would put in a natural gas plant or a biomass burning plant. And the idea is you would capture the carbon dioxide in the flue stack, and then as a gas, compress the gas, and then put it in the ground someplace like a reservoir rock and store it. There are two problems. One is once you take fossil fuels out of the ground and burn them, you're basically blowing them up in volume by a factor of 4 to 10. And now you're trying to stick that back in the ground. And when you stick it back in the ground, you've got to hope that it doesn't leak. Because if it leaks, it might leak in a big burst of carbon dioxide, which would be bad, right? You'd have a big effect on the climate. Finally, agriculture has got, as we said earlier in the Gates notes slide, agriculture has got an issue with various carbon emissions, nitrous oxide emissions. And there are lots of ways to go about this. There is no-till or low-till farming. This is where you don't churn the soil over very deep, because as soon as you do that, you basically release a lot of carbon in the soil, and you expose the soil to leaching from heavy rain or from drying out with high temperatures. You grow cover crops, so in the winter, when your production crop is not in the field, you have it covered with a crop that protects the soil, helps it protects it from erosion, also creates some carbon capture in the roots of the cover crops. Crop rotation, so you're not growing the same crops year after year. Even if you're rotating between corn and soybeans, that's not really a very effective rotation at replenishing the soil. People have used lentils in rotation and various other rotation crops, which make farming soils more carbon rich. And that would reduce costs because you'd be able to use less fertilizer and so on. So we don't have to we got to make farming more resilient, more efficient, not just more resilient. What I mean by that is resilient means that the farms will be more stable and they will be able to handle changes in temperature and precipitation better than they do today. But we also need to realize that these farms grow a lot of food and they need to continue to do that, right? Otherwise, we'll have a problem with food production. There are lots of good ideas out there for agriculture. Large monoculture farms, which the Midwest of the United States is really good at, single crop farms, mostly corn, soybeans, will have to undergo the most significant changes. And so there's a lot of work to be done there. So that's where I wanted to leave that. We are going to in lecture 11, talk about a proposal, with this background that we just talked about. We're going to talk about a very specific proposal with some ideas about how we might go about this. Again, it's kind of a straw man proposal. And then we're going to summarize the course. So thanks for being here again, and we will talk to you soon.